Okay, I think it's time to start the class. So if you'll please take your seats and give me your attention. Gentlemen in the back, I'm speaking to you. Gentlemen, it's time to start the class, so let's please cut the conversation. Thank you very much. Okay, if you remember, we are building a processor unit by going through the instructions in our instruction set architecture one by one. We're translating them into register transfer languages, and then we're seeing what structures we need to support those register transfers. We've been noticing an interesting thing called control lines and control points, but we haven't studied them systematically yet. We're just seeing what we need in our data path. And you've noticed that there's two main things that we need in our data path. We need the structures to operate on the data that begins in register and ends up in either register or memory. And then the second thing, when we started working on the conditional branch, is we noticed we need to have a way to change the PC and give it either PC plus 4 or PC something else as its next value, because change of control is what branches and jumps do. So we got through the branch. We showed a slow way and a fast way with less hardware and with more hardware to implement the change in PC. And that was the last thing we did. And so one instruction is left. We've covered 8 out of the 9 instructions in our little subset, and we need still to do the jump instruction. So that's where we left off. That's kind of the review of where we were. I hope you were here last time. We covered a lot of ground in Chapter 4. If you're not coming to class on a regular basis, shame on you. You really need to be here every time. This is sequential material, and if you miss even 1 2-hour lecture, I cannot help except to say, I'm sorry, but you're kopmush, and yakalamak will be very hard. To catch back up after you miss will be very hard. So please focus. I know that midterms are coming up next week, but people don't cancel classes just because of midterms. So please come to class anyway, and don't say, Bosch fair class, I studied for the midterm, that's enough. Then you're going to be punishing yourself for the final exam because you didn't come to the class at the crucial time. Okay, the second half of the course is the hardware half. We're at the beginning, we're laying the TML for the hardware. Everything we're going to do on top of this about pipelining and memory and multiple processors and I/O depends on this. If you do not understand why we have this data path and control the way we do, you're just going to lose the second half of the course. So tell your friends, get back in here. We're supposed to be 50 people here. I don't see anywhere near that. So they're making a bad mistake. I don't take attendance. We have quizzes from time to time, but the point is you're going to see what you know on the exams and on the projects. If you don't know anything, you cannot help your group and you cannot help yourself. So I know I'm preaching to the choir, off-errand for all of you to be here today, but there's a lot of people that should be hearing what I'm saying, and they're not here to hear it. So please do me a favor and tell your friends and tell the people in the missing seats to please come to class. Okay? So I'm just trusting that you're mature enough that you realize my job is student. You know, my job is teacher, your job is student. It's your job, Okan. Your job is to be a student. So what does that mean? You come to your job, you do your job. You know, this is your work. In a few years, your job's going to be something else. But right now, your job is student. Okay? Oh, I like everything about university except the academics. Wait a minute. What are you doing in university? Oh, the activities are great. The campus is super. I love the friendships. We have a lot of fun. Wait a minute. Whoa, 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 whoa. A student means there's something to study. It comes from the same verb as study. Yeah, you think that's very funny, but you know that there's a lot of people take that mindset. You know, academics Harwich, university super. Wait a minute, but what happened to the Harwich part? That's supposed to be the core of the university experience. Okay, let's go on. So our 9th instruction that we're going to build into our data path is the jump instruction. It's got a very simple syntax. Remember J and the target address. We're using pseudo-direct addressing. So here's the register transfer statements that come from this instruction. We've got to access memory. We've got to change the upper 30 bits in our program counter to be 26 bits of my target address and 4 bits taken from my current program counter. The upper bits, that's why we call it pseudo-direct. This is the direct part, but this says actually where you are in that range is the range that will still stay in. The upper bits stay constant. And you notice that's only 30 bits, and you say, wait a minute, what about 32? And if you weren't here last time, you missed a very important point. We said the last 2 bits in addressing are always 00, because addresses of instructions, not data, but instructions, always begin on an even word boundary. So therefore, there's no need to have 2 more bits here which are 0, and 2 more bits here which are 0. We'll cut them down, and that'll enable us to save hardware and make the registers smaller and make the hardware faster. So here we go. We've got a 6-bit field here and a 26-bit field here, which is the target address. There we are. And we append, that's the appendage operator, 4 extra bits from the upper bits of the current value of the PC, and that's the new PC. So we change the old PC to this new PC, and that means we jump there, we go to there. So to do that, I'm going to have to modify my next address, or my instruction fetch unit. IFU stands for instruction fetch unit. We're really not doing anything in the proper data path. We're doing something in this instruction fetch portion. Now, if you were not here last time, get me Scholzen. There's a lot of complexity up here that we discussed last time, and so we're going to add something new. The red is the new. Before, what was already up there was the hardware to do PC goes to PC plus 4. That's our sequential incrementing of our PC to the next instruction. And the rest, and that's the top, and then the black part down here, I'm sorry, that's not totally true. Most of the black part down here is the branch hardware in order to do PC goes to PC plus or minus an offset. Okay? But now the red stuff is for PC goes to pseudo-direct jump target address. Pseudo-direct jump target address. And let's see how we do that. We take the current value of the PC and we peel off the upper 4 most significant bits. And we're going to concatenate those with the 26 bits from the instruction itself. The instructions field's target 26-bit field comes together and we form this 30-bit address. And now with these 2 multiplexers, I think you can see we have 1, 2, 3 choices, and the proper codes on these will choose 1 out of those 3. And what are the 3? PC goes to pseudo-direct target address if it's a jump. PC goes to PC plus or minus the FARC if it's a branch that we take. Otherwise, PC goes to PC plus 4 if it's a branch we don't take or if it's a regular instruction, non-branch, non-jump. Those are the 3 choices. And you can see here's the one where the pseudo-direct target address for jumps comes in. If we say jump, take it. If it's not jump, we'll take this one, which is one of these 2. Here's where PC plus 4, if you know what I'm talking about, PC plus 4 comes in. That's our standard increment to the next sequential instruction, or don't take the branch instruction. And finally down here is the branch target address, which is PC plus 4 plus the immediate field sign extended into a 30-bit number to be added together with that, right? So that's the take the branch, plus or minus immediate. Now why did I say 4 and it says 1 here? Because we've dropped 2 zeros from everything. 30 bits, 30 bits, 30 bits, everything's 30 bits. We're not dealing with 32 bits anymore. Why should we? The last 2 bits are always 0. Let's squeeze it down and make it smaller. Okay, so that's why it says 1 here. But in fact, it's taking the PC's byte address and incrementing it by 4, or you might say taking the PC's word address and incrementing it to the next word. Okay, so there we go, a 3-to-1 MUX combination. It could be done with a single 3-to-1 MUX. It's shown here just for simplicity as 2 sequential MUXs. This is actually not very fast. This is going to be 2 levels of delay, 2 levels of delay, grand total 4 levels of delay. We could certainly do it better with a single MUX with 2 levels of delay, couldn't we? We know about things like that from taking CS-224. That's why it's good that you have the digital design course. You understand about delay inside these units. Okay, so there's the open architecture. In the end, that will produce something coming out of here which we load into the PC, and that's the value of our next PC. Whatever it was, we're changing it into either this or this or this. So this is called the instruction fetch unit because that value of the PC, as you can see, goes to the instruction memory. As a 30-bit address, we stick on the extra 2 zeros here. It's a 32-bit address, and that says, give me my instruction. I need to send it to be decoded and used in the data path. Yeah? So all this is just to create the correct value here to fetch the instruction. Okay? So if you don't mind, I'm going to go back a little bit and say that from where we started, which is right where did we have it? We had a little there. It's right here. This got a little more complicated, didn't it? It's not just PC goes to instruction memory. There was a whole lot of stuff that we just had on the last slide. So this portion is the instruction fetch portion. Once I've got it, it goes to the decode, get operands, execute, and store back the result section. Okay? Remember in our total cycle of, where was it here? Total cycle of instructions? Fetching's part of it. And now you just saw the hardware necessary to do the fetching for regular instructions, branches, and jumps. Then we've also seen the hardware to do this stuff, okay? That involved the ALU, the register file, the data memory. So now there's a relationship, isn't there, between this and that hardware. There's also a relationship that we've built, as you know, between every one of these. Okay? Every one of these instructions requires hardware. Even when we get to the branches and the jumps, they require hardware. Okay, now we've put it all together in this slide. So here's our full data path with the instruction fetch unit shown as just a box, but the inside of it, of course, is what we just showed. So this is the instruction fetch unit. It takes, are we branching, are we jumping? It needs a clock because it has the PC register inside it. It takes the value, is the FARC 0, so that's helpful when we're going to branch. And out of that pops the instruction. Okay? Inside it is the instruction memory, so the instruction address is given to the instruction memory, and out pops the 32-bit instruction. And we send pieces of it to lots of places. The RT, the RS, and the RD, they're going to places over here. The immediate 16-bit field is going to here. And we also have to have a clock that goes to any place that has a registered storage, such as here for the PC, here for the 32-bit registers, and here for the memory with its thousands of registers or millions of registers. Okay? So we need clock circuitry for those three. That means they're sequential. And what does that mean about this box, this box, this box, this box, and this box? What does it mean about those? They're combinational. They have no clock. They're simple combinational circuitry. Inputs now determine outputs right now or a little bit later if you add realistic gate delay. Okay? Remember all those lessons from CS-224? I'm just reminding us of what kind of hardware we have up here. A mix of sequential and combinational. Therefore, a box around the whole thing says that's a fancy sequential circuit. It has state. In fact, it's got a few states. It has state. And we haven't even got to the control unit yet. This is still the data path. Yeah, okay. So data path has state, but its state is register values. Okay? We certainly have to have clocking for this. So you can see why register transfer language is such a perfect language to express what we want to do here. I want to take a couple things here, do something with them here, and stick them here or stick them back here. Right? All under clock control. And then I want to know what the next thing to do is. Well, that's coming in my instructions. So obviously the control unit is going to have to be sending signals to there and to some of these. And we've got some control signals. Look at them here. Mem to reg, mem write, ALU source, external operand, register write, register destination, branch me, jump me. Okay, we've got a lot of them. Those things in blue we haven't yet designed. They're part of our control unit. We're going to have to do a second half of the design and do that. Remember the 5 steps in the design? 5 steps in the design. The first 3 are about about the data path, and the next 2 are about the control unit. And number 6 was about iteratively improving it and testing it and getting it faster and getting it all worked out with timing and real circuits, etc. Right? So the design phase is actually the first 5, and then implement and test is number 6. And just as a little footnote, I hope you're heavily into the implement and test part of your project number 1. You've done the design phase, you've done a design review phase, now you should be deep into implement and test phase of project number 1. It's due Monday, by the way, just in case you didn't know. Okay, now let's put it together. This is a real data path. As you can see what it is, it's a micro photograph of the circuitry on the MIPS data path. We don't have control shown here, but let's see what we can read here. It's in your textbook as well. CPU reg, I guess that would be the CPU registers. CPU BYP, not quite sure what that is. SMD, not quite sure what that is. CPU add, CPU control. So here's some kind of adder unit here. CPU lush, it looks like CPU LUSH. Not sure. Add gen, that's address generation. What do you think that might be? Remember what we called instruction fetch unit, generating the next address. There was a bunch of hardware. That's that block right there in order to figure out what the value of the PC should be next, the address generation. Here's MAGen, that stands for memory address generation. And a little here in the corner, CPU control. So there's some CPU control there and some CPU control there. Oh, I'm sorry, this is PC gen. That's the PC generation. So this is some other kind of memory address generation. And then there are these things that look like weird noise from outer space. Those are actually transistors photographed from the top of a chip. Okay, looking down, you can see they're very dense and they're fairly regular. I don't know if you can tell here, but something along here, something along here is different than the material here. Whatever we're doing here, we seem to be repeating it tremendously. This is a little more random here, okay? So the idea is regular structures, good layout, fast buses, connection of things that need to be nearby each other. So that's called a floor plan. The layout is based upon a floor plan, how to use the chip area effectively for fast circuitry and for effective signals to be communicating quickly with low noise, with minimum power rather than maximum, it's minimum interference, etc. So that's the floor plan. And then the actual, when you zoom in, you've actually got, you know, transistor layout and cell layout on a micro level inside here. Okay? So that's just for your information. All right, I'm ready to start to design control now. We've done a data path design. We understand what the blocks are. Go back to 223, you know how to build every one of those blocks. So there's no need to go inside the blocks now. We're working at a level of abstraction called block diagram level. So we've got major blocks. We understand how they're connected. We see how they implement the instructions. So I'm ready to go on to control, but I'm wondering if you are. Are you ready to go to control, or do we need to work more on understanding the data path? If you have questions, I'll be very happy to slow down and we'll go back and just work more on the data path. Remember what we did? 9 instructions. We worked each of them into register transfer language equivalent. We saw what therefore transfers are needed and what blocks are therefore needed to do those register transfers. When we got to branch and jump, we realized we better do something a little more intelligent than just add 4 to the PC, because we won't be able to branch or jump if that's all we ever do. We'll just go duh, 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 duh in sequence. So we added some instruction fetch unit hardware as well, or next instruction unit hardware as well. When we got it all done, we put it together, we saw that actually it's understandable. You know, if anybody here is afraid and beginning to get nervous and have, you know, panic attacks looking at that, please raise your hand and let me know. I'll give you some tranquilizers and help calm you down. This is not something to be afraid of as computer engineers. The block diagram of a processor unit, at least the data path part. Then we're going to do control, and you're going to find out that's not so scary either. But I just want to hear from you. Are you okay? Are you good? Remember last time, Emerson, are you good? Does anybody here have objections or questions or feels kopmush or doesn't understand what they're looking at? You know, basically I'm asking the question, when you look at that, do you understand it to a high degree, 80, 90, 95, maybe 100%? If you're less than 80, you say, no, there's just too much there I don't get, then let's go over it again. Let's go over it again. I'm here to help you learn. I'm your learning assistant, right? You're the learner. That's the active role that's expected from you. I'm the learner helper, okay? I don't think I can teach anybody anything. I think learners can learn. I'm a total believer that the responsibility is on you. I'm here to interpret and make it your learning as smooth and as easy as possible. But I don't believe in open brain, teacher dumps in, thank you, we've learned. There's no such thing. And that just doesn't exist. So active learners, as you put your mind on that, do you understand what we're looking at? If not, we'll go back and build it again piece by piece slowly. I mean, remember, this is built up too. This is not pot d'A. I don't believe in that either. I believe in understanding what we're doing step by step. So we got here step by step. And the question is, did you follow the steps? Are you okay with where we've come to? Not really okay. All right, good. An honest man. An honest man. Give him an award. Okay, thank you for your courage. All right. Does anybody else agree that they're not okay? All right, we've got number 2 here. 2 honest guys. The rest of you are liars. No, that's it. All right, I'm happy to roll back, and I'd just like to know how much rollback should we do, or is there any particular area that you're not so sure about? What's instruction fetch unit? Okay. Okay. Well, that's the last thing we did. So let's begin by saying, what did we think the instruction fetch unit was? In the beginning, way back, we said all we need to do is have a PC that gives its current value to an instruction memory, and this is the instruction address, and out pops the instruction stored at that address. This is memory. So you give the address, and out comes the thing stored, and it's the instruction. It's a 32-bit field, and so some of it is these registers, some of it's immediate, blah, blah, blah. Remember, some of it is the actual opcode itself. So that was our real simple model. And then we said, yeah, but that always gives the same value. Does anybody notice this just stays static? It doesn't ever change. So we said, let's upgrade that a little bit. Let's have a way for the PC to add 4 to itself and become a new value. Okay, so we take the PC and we send it to the instruction memory, and out comes the instruction. That's the same. The new stuff is this. I'm sorry it's not in red, but the new stuff is, oh, and also at the same time, send it to an adder which adds 4, and on the clock, bang, now it's PC plus 4. So now we have the ability, after every fetch of the instruction, or together in parallel with the fetch of every instruction, to change the value of the PC to make it the old plus 4 bytes more. So that's great. That means we can do code like this. This one, then this one, then this one, then this one, then this one. Lovely, but it doesn't allow us to do any looping, branching, jumping, if-else casing or anything like that. It just says do, 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 do. There's no conditions here. There's no go-tos here. So I'm sure you remember from CS-101, David must have taught you that in order to be able to execute algorithms, we got to have the ability to change control. That's a fundamental feature of the program model. So if we can't change control, we cannot execute all. There's a lot of things you can do with bang, 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 but there's a lot of things you can't do. Some of them need this, some of them need this. We got to have that ability. So we're short on branching and jumping. But for now, that's the model of our instruction fetch unit through add, subtract, register, or immediate, immediates, loads, stores. All these just simply say do this and go to the next one. Everything's great until we come to branch. Now, the problem is it's too simple. It doesn't do what we want. Because branch says, if we take the branch, the new PC is this. If we don't take the branch, the PC is this. Okay, that's great. We have that, but we don't have anything to do this. And we need this. Now, everybody stare at this and make sure you understand the syntax of the register transfer language. Why is it that taking the branch means do that? Do you know? Remember, we said branches are PC relative. That means from where you are right now, you're going to go relatively backwards or relatively forward, some FARC, and that's going to be the new address of the next instruction fetch. So it means take where you are right now and add to it the sign extended value that's stored in the immediate. And we're going to multiply it by 4 to add 2 zeros on the end. And we're going to notice that, well, we've already incremented by 4 anyway. We always add 4, so never mind. Just, if you don't want to go, let's say the PC is 20 and you want to go to 100. Okay, so the difference is 80 bytes. Well, PC is already now 24, so you only need 76 bytes. So you make this 76 and you'll still get to 100. It doesn't really matter about that. You can compensate this to make up for that. So, if this is the standard model, then just add this to it, and that lets you go relatively forward or backward. So we need hardware to do that. If you want to get to 100 and you're at 20, you need to branch forward 80. Or if you're at 20 and you've already got it at 24, you need to branch forward 76 bytes. So therefore, we got to have hardware that'll change the PC not by 4, but by 76 plus 4. Got to have hardware to do that. That's what this is saying. This is what I want. Hey, where's the hardware? The old hardware I showed you is not going to do the job. So let's add some new hardware. Buyurun.
Why do we have to put 2 zeros at the end of the address?
We don't have to, but I'm going to tell you a good reason to do so. This already ends in 2 zeros, and this already ends in 2 zeros. And therefore, if I add something that ends in 2 zeros with something else that ends in 2 zeros with something else that doesn't end in 2 zeros, I'm going to get a sum that doesn't end in 2 zeros. Do you agree to that? Okay, if the sum doesn't end in 2 zeros, it's a non-aligned address, and I'd be foolish to try to fetch an instruction from there, because all my instructions are located at addresses that end with 0, 0, like 4, 8, C, 10, 14, 18, 1C. So therefore, I don't want to fetch anything from an odd address. It's got to be an even divisible by 4 address. Tamam, you agree to that? Yeah, okay, great. So therefore, since this would have to be ending in 2 zeros anyway here, my question is, why just use 14 bits and waste the 2 every time when you could use 16 bits and have a greater range to jump forward and backward if you automatically stick on the 2 zeros sonradan? Let's don't waste our bits, our valuable bits, doing useless things. Let's instead add the 2 zeros on later. That's what we're doing. We're adding the 2 zeros on later. This becomes now a full 16-bit range of 202 to the 16th power yani, 65,586 or whatever it is, different possible places to go to. And those are word addresses. As soon as I stick on the 2 zeros, now it's byte addresses. Tamam, that's the reason, is to use this as fully as we can. And that same answer is the answer to why we stick on 2 zeros in the jump address, to be able to use the bits as completely as we can to have the largest possible range to go forward or backward in the branches or the jumps. Okay? So that's the answer to that part. Okay, given that you need to do this, and we don't have the hardware, or you might need to do this and we do have the hardware, I think we've come to the conclusion we need to improve the hardware for fetching the next instruction. Yani, changing the PC. Okay? If you go back to here, we can fetch the next instruction as long as we have the right value of PC. So this part doesn't need to change. The problem is this doesn't give us the right value of PC when you take the branch. So this part's going to have to change. In the end, the PC will go to the instruction memory and out will come the 32 bits. So now we've motivated the need for why this needs to be more complicated. Were you here at the last class? All right, then you remember that we then said, okay, great. So branching needs to be able to do something interesting. So we need to look at the following. Not this. This is the data path computation part. This is the next instruction stuff. And look what we're doing. The ALU, after it subtracts two things, says, are we going to take the branch, yes or no? And the 0 signal is the yes or no, if we're going to take it. So if we've got a branch instruction, and if my ALU is telling me take it or don't take it, and I have the 16-bit immediate, which I'm going to use in the equation, multiply it by 4 to get the 2 zeros and add it to PC plus 4. Here's PC. So I've got all I need to make this box work correctly. Okay? Now, what's inside this box? So if you see here, I'm going to expand it even more. In the end, what pops out of this box is the address that goes to instruction memory. Yeah? Everybody see this here? It's not just take PC and add 4 and put it in the next PC. It might be, if we don't take the branch, but it might be something a whole lot fancier, like take the PC, add 4, add this thing multiplied by 4, and put that in the PC. Yeah. Okay? Yeah, that's what it might be. So this is a halfway step to the next slide, which is the full Monty. Okay? Don't be scared. Hang on to your chairs. Here we go. Oops, it's not there. It's there. All right, now here we go. Now we're saying fast, expensive, next instruction fetch. That's not if, that's instruction fetch logic. Whoa, there it is. But everybody sees that in the end, the PC says go to instruction memory. And since it's only a 30-bit PC now, we've got to add on the 2 zeros. But we already know why, because I just convinced you that we never have anything here except chief cipher if we're going to get an instruction. Data, yes, I can get a data byte or a data half word. They can be all over the map. But instructions have to be like soldiers. They've got to be in their spot lined up in memory. Okay? We don't ever have shifted instructions. Ooh, tu hafpierde yerleshtil mishnosuliani napolum. It doesn't happen like that. Okay? They've got to be on even word boundaries. So that's very logical. So this is what we showed before. The PC goes to instruction memory and out comes your instruction. The part that's interesting is now how do I calculate the next PC? And everybody can see, if you look close, I've got a mux here. And coming out of that mux is the thing that goes into PC. So that means this is called next PC. I haven't loaded it yet till the clock comes, but when the clock comes, bang, it's now my next PC value. It's my current PC value then. Right now, when it's sitting here, it's my next PC value. Well, what does a mux do? A mux chooses between two alternatives, right? Got two possibilities. Either I take this or I take this. What's this one? This one is coming out of an adder that says take the current value of PC, the 30-bit value, and add 1 to it. If you like, I could make it a 32-bit value, and then I'd have to add 4 to it. Oh yeah, PC in bytes plus 4 is the next location of the next instruction to fetch. Instead, let's take PC in words and add 1 to it. So you could say this is the sequential next address. So since we're discussing what happens if you branch, all of us can guess ahead a little bit and say, oh, well then that must be the branch target address. And we'll decide to take it or not based on a decision of the mux. So what will we decide? Well, if it's a branch instruction, and if the difference between the two registers you're comparing is 0, it means they're equal. And so if it's a branch, if equal, and they are equal, then you should take the branch, which means take that one. But if either of those is not true, you should take that one. Okay, so there we go. Now the last little bit is, let's look back this way and figure out how did we get PC plus 4 plus the immediate sign extended shifted by 2 bits, two zeros. And if you look at that, you'll say, well, it doesn't do that. It takes PC plus 1 plus the direct sign extended 16-bit. It doesn't do any 4s. There's no multiply by 4. There's no add 4. You're exactly right. And now I'd like to toss the ball back to you and ask you to think, why is that we're not messing with 4s anymore? How come we don't take this and multiply it by 4 and then sign extend it? In fact, we just take it as is and sign extend it. And how come we don't add 4 here to the PC value, add 1? Because everybody can see that this right here is PC plus 1 plus the sign extended immediate 16-bit value. So if you can ask yourself that question, and if you're able to understand why it's not exactly this, we got rid of that 4, got rid of that 4, you understand it very, very well. So let me pause now and ask, do you understand it to that level? Why are we dealing with 1s instead of 4s? This says 4 twice. Over here, there ain't no 4. So what happened?
At the final step, we add 2 zeros. So instead of we just multiply everything by 4.
Exactly. Exactly. The whole thing generates a 30-bit address, and we stick 2 zeros on at the end. If you take this off, now everything has to be 32 bits. All the buses, the muxes, the adders, everything 32 bits. And that means that this has to be 4, and this has to be multiplied by, 4 before we sign extend it. 32 here, 32 here, 32 here, 32 bit. Yeah, it just makes everything bigger. So a very clever solution. Thank you for pointing that out. Just shrink all that and stick on the 2 free zeros at the end. Yeah, that's a very clever thing to do, isn't it? Boy, computer engineers are just clever, clever people. They're so smart because they always are looking for ways to get the right answer more efficiently. Remember, I told you in 223, it's not just about getting the right solution. It's about getting the right solution, which is the best answer among all the competing factors, such as, in this case, size and speed and cost. Reliability, power, customer satisfaction, usability. There's 100 different factors that compete. But my solution works is not good enough because the next engineer over at the next desk or in the next company says, my solution works and it works better than yours. Oh, well, then maybe just working is not good enough. So we see an improvement here. Okay, that's the end of the branching. If you'd like, we can move on to jumping. And watch close. See that model? We're going to just add one new red thing. Do you see now it's a single mux with 2 inputs. Let's go to jumping. Now it's 2 muxes with a grand total of 3 inputs. The new stuff is the red. All I did was keep that the same, and what was the choice before between sequential and branch address now becomes the choice between jump, sequential, and branch address. So there's the jump address, there's the sequential address, and there's the branch address. I got 3 choices. I do it with 2 muxes R to R. That's not so good. Or really a 3-to-1 mux would be better. Everybody know what a 3-to-1 mux is? 3-to-1 mux. This looks like this. I got 3 inputs, 2 controls. I choose 1. That's a 2-level circuit. That's a 2-level circuit. That's a 2-level circuit. So therefore, that's 4 and that's 2. This is better. It's clearly better. What does it mean that's a 2-level circuit? Hoja, I didn't understand that. 2-level dynamic, Hoja. Why are you here? You had to pass 223 to get here. If you don't know what a 2-level circuit is, I made a mistake. You shouldn't be in this class. Raise your hand if you know what a 2-level circuit is. Raise your hand if you know what a 2-level circuit is. Raise your hand if you know what a 2-level... I'm trying to avoid asking the other question. Raise your hand if you don't know what a 2-level circuit is. So let's see if you know what a 2-level circuit is. All right, and those of you that don't, keep your hand real low so I can see who you are. All right, I didn't do such a great job because I was hoping for 95 to 100% of what a 2-level circuit is. All right, you know what a 2-level circuit is? What's your name? Fuat, would you like to tell the class in a loud voice what a 2-level circuit is? Well, then, never mind. Okay, I need somebody who knows how to explain. Knowing what it is okay, but knowing how to explain it's even better. Who over here knows what a 2-level circuit is? Hey, there was a lot of hands up earlier. Now they're all down. No fair. No fair. All right, Okan, I'm going to pick on you again. Explain in a loud voice what a 2-level circuit is so everybody can hear.
If we put 2 inputs in one gate.
Loud voice.
If you put 2 inputs in one gate and after this calculation or this result, to put this value and another value in another gate, It's meant 2 level.
Okay, he called it a 2-level. Is it 2-level because this is 2 and this is 2? Or is it 2-level because this is 1 and this is 2?
Boundary signal has 2.
Yani, Okan, I'm just asking this. Can I do this? Is it still a 2-level if I do that? Yeah, it's not about the number of inputs. It's about the number of levels. That's the first gate level. That's called the second gate level. If I'm done with the function here, if these are the overall inputs, and this is the overall output, it's a 2-level implementation. It's a 2-level circuit. If I have 3, it's 3-level. If I have 4, it's 4-level. If I don't know how many, it's n-level. Now, what's so great about 2-level circuits, according to George Boole? Sanem? I let you in this course because you promised me you learned it well in Scotland on Erasmus. Okay, what according to George Boole, what's so great about a 2-level circuit?
I introduce the inputs which we use the gates.
Oh, I don't know about that. I can probably think of a 3-level that has less gate inputs than a 2-level. No, I don't agree. That's not what George Boole would say. What's so great about 2-level? Pardon? Yeah, 2 levels faster than 3, but you didn't need to ask George Boole for that. All of us can see that. Why is it faster? Does this have a finite delay? Does this have a finite delay or an infinite delay or a 0 delay? Finite delay, right? It's non-zero. So therefore, if that's non-zero and that's non-zero, and I don't have any levels that can give 0 delay, I promise you 3 is slower than 2. We all can understand that. No, that's not what George Boole would say, though. What did George Boole say about Boolean switching functions? Come on now. Theory and practice have to stay connected. Please, friends. George Boole said, any Boolean function can be implemented in 2 levels. It never requires more unless you want to make it slower on purpose. If you have reasons, you can make it more, but we can get the job done with 2 no matter what the switching function is. And that no matter is an enormous universal claim. That means I can do floating point square root in 2-level. That means that anything can be done in 2-level. Why? And, or, sum of products, or, and, product of sums. George Boole says, that's it, man. That's a universal set. There ain't no exceptions. There's nothing that you can think of that can't be done in 2 levels. They can all be done in 2 levels. And the back row just said, and 2 levels is the fastest. So if they can all be done in 2 levels, and 2 levels is the fastest, how come we don't do everything in 2 levels? How come we don't do everything in 2 levels? Yeah, George Boole didn't remember to also say, but it might be really big. He didn't say that. Okay, so the question is, this is 4-level, and this is 2-level. Is there anything to be gained by doing it that way, or lost by doing it that way? Possibly size and space. Possibly. You have to look at it. You know, what's the gate input count of this and the gate input count of this? But I tell you, I've done this before. This one's the winner. There's no reason in the world to do that except for pedagogy. Does everybody see why that's been done that way? Because we had that. Instead of changing it completely, let's just help remember what we had and add one more. So we just added. But that's actually not good design. The first thing that an engineer would do is say, whoa, I see a great opportunity to shrink some stuff together, and I see another great opportunity to shrink some stuff together. Yeah, you would work on minimizing that, wouldn't you? To speed it up. If instruction fetch was on the critical path, and it was part of keeping the computer slow, you would speed it up. But if instruction fetch was already plenty fast and the problem was in the data path, and you had slow ALU and slow register fetch, then you would say, why am I wasting my time on this? I want to make the slowest case faster because it's on the critical path. So, you know, obviously you would use your engineering manpower wisely to know where to invest it for speed up. But I see some good candidates for speed up right here. We've already shrunk the size down by making everything 30 bits instead of 32. That was a big savings. All right, so now let's put all together. And did we do the jumping too? Yeah, we did the jumping too. So then we did this, and then we did this. And then I said, are we ready to go on to control? Do we understand data path now? Do we understand that now? So we had a lot of work on this. But nobody asked any questions about that yet. Yeah, sure, you can ask anything you want. We stay here all day for 2 hours. I don't mind. We come here next week and work on some more if we have to. This is really important. I'm not, kolay hafif geçmeyeceğiz.
I understood what the hardware done, but I had a confusion the software translation in hardware. and branch and jump instructions.
Okay, so yeah, how did we translate these softwares into these hardwares? Okay, great idea. Can I do an example for you? Okay, like store or load, or go ahead, yeah.
For example, we have a loop, that loop and semicolons.
Okay, so for I equals 0, I is less than 10, I plus plus. Yeah, okay.
We translate in MIPS.
Translated to MIPS. Okay, so at the MIPS, what I'm hoping to do is have a branch not equal at the bottom and go to top. And top says you got to come in the loop one more time and do this. And I is equal to 0 before I enter the loop. And inside here, I is equal to I plus 1. So there's my loop control initialization. There's my loop control increment. Right here's where I'll be testing the loop control. And everything else that I do here is also inside here. Yeah, okay. So I've got a branch, and that's all. I didn't use a jump. Okay, go on.
And we write somewhere in my code, jump top, for example.
No, I have BNE top.
Yeah.
Branch if not equal to top.
Yeah, but an external code.
Oh, somewhere else. Jump top. Well, the problem with that is you're coming into a loop before you initialize the loop control variable. That's terrible. We would never want to do that. Why would we come into a loop and miss the initialization?
Let's write this code, for example.
Let's write it. Oh, well, okay. We're on dangerous thin ice here. You want to, yani varsayalım ki çok tuhaf bir kod çıktı. Yani compiler yanlış yazıldı ve yani yazan kişi işini bilmiyor. Öyle varsayalım. Okay, tamam, but I'm going to be really careful about that because it's weird. Why would we write bad code? Why would we allow a compiler to write bad code? And why would we let a user write bad code? You wrote some bad code, but this weekend when you test, you're going to find the mistakes and fix them. Değil mi? Yani it's going to crash. This is not going to work, obviously. So gerçekten bunun üzerinde konuşmak istiyor muyuz? Yani gerçekten yani olmaması gereken bir şey hakkında konuşalım mı? Yani that's my problem. Is I don't.
My confusion is two codes do the same thing. How they convert to hardware? My question is that.
How about if we do this? We jump to top 1. All right, now I'm a lot happier. Now because it's going to enter the same loop. So in a sense, this loop had the name top. Okay, so you want to do the loop, and you're entering into the loop from somewhere else. So now we're entering the loop from here maybe, and we're also jumping to it from somewhere else. And your question is what? Your question is what?
My question is if two codes wants to jump the same location. Top.
Yeah.
Not top.
Yeah, okay. I don't know what to say. I'm having a little trouble understanding your confusion. Let's try to remember that assembly codes translate into machine codes, okay? So here we go. Now it's literally ones and zeros in some section of memory, okay? And so the address here, 48, happens to be what top 1 is equal to. So if you go to here, you went to top 1. So what does that mean? Initialize I equals 0, then do the body of the loop. Down here, the last thing is the branch. Yeah, okay. So now the only question that you're asking me is, can we have J48 here? And can we also have J48 here? And why not? Why can't I call this loop from this part of code and run the loop, and also call the loop from this part of the code? What's wrong with that? Is it yasak? Do you have a reason why you think that's yasak?
Not, but the instruction is different. One of them branch instruction, one of them jump instruction. And
Yeah, of course.
takes 26 address bit, and branch instruction takes 16
Now I got it. Now I got it. You're trying to ask, how can I branch to top, and how can I also jump to top?
Yeah.
Ha, okay. Great. All right. Let's answer the question, okay? A jump uses what kind of addressing? What kind of addressing?
26
There's a name for it. Starts with PS. Huh? Pseudo direct. Yeah. So that means that the value here, if you want to know what the machine language bits are going to be, is the opcode for jump, which is, some code 0110, okay. And then this value is going to be what? You tell me.
46.
Huh?
46.
Why 46?
48.
Yeah, essentially 48, because that's what top is. Okay, great. So what do we do with this 48? We actually, it's not going to be 48. It's going to be 12. Can you know why? Remember the 2 zeros on the end? Okay, so it's 12, but it turns into 48. But 48 is only 28 bits. We're short 4 bits, so what are we going to do also? Yeah, not so, no. Okay. What happens on jumps? What happens on jumps? How do we get the full 32-bit address on a jump? We take the highest order 4 bits and we concatenate. Do you know the meaning concatenate? Do we know the meaning of the English verb concatenate? Yapıştır, right? Just like with to call. Two things, paste them together. Okay, you can see that this is the upper 4 bits. This one starts at a lower place. The grand total of those concatenated together is 30 bits, right? There's 4, there's 26. Paste them together, you have a 30-bit object, okay? So that means that this needs to have concatenated to it that much, right? Okay, so we go to that. Okay. Now you're asking about this one. How do we do branch not equal to top? How do we go to that 48 here? Well, if this happens to be 64, we use a different kind of addressing on branches. Do you remember what that's called? It doesn't start with PS. It starts with PC. PC relative. It's a different kind of addressing, okay? Now, what's PC relative addressing? What's your name? Fatih, can you tell us what PC relative addressing is?
We find the address according to the PC. We give the difference between.
Yeah, that's a very nice idea. What's the Turkish word for relative? Bal. So relative to what the PC is now, what's the fark? I don't say where I want to go to, I say what's the fark I need to get there, all right? So what's the fark that I need to get there? 16. So I wouldn't expect 16 here, except that actually, when I get to the code here, this immediate field, I don't write 16, what do I put? 4. Why do I put 4? Because there's going to be 2 zeros appended onto the end anyway, yeah, by the hardware, okay? So this 4 means 16, and so what am I saying? Actually, it's negative 16 is what I need. Can everybody see what that does? It says take the PC and subtract 16 from it. So 64 goes to 48. Now let's fix it just a little bit more. If you really look at it, it doesn't do exactly that. It does this. It says take the PC and add 4 to that and then add this on top of that. Oh, well then it means that I want to start my calculation at 68. So this needs to be 5 in order to get 20, because 68 minus 20 is 48. All right, so I hope I've answered your question by showing that jump and branch have 2 different addressing modes. One uses PC relative addressing, one uses pseudo direct addressing. All right, my friends, now we're going to have a little review. There's 5 addressing modes in MIPS, and you've read about them in the chapter, I hope. And I asked them on a quiz, I think, or some of them on a quiz. What are the 5 addressing modes in MIPS? 2 are for next address, and 3 are for data operands. Where are the 3 places that we can get data from to operate on? Registers is one, memory is another one, and the instruction itself is the third one. If we get the data from the instruction, what kind of addressing mode are we using to go get it? Immediate. If we get the data from the register, what mode are we using? Register mode. If we get the data from memory, what mode are we using? Base plus displacement, right? Remember, there's a base address which is contained in a register. You add some displacement, and maybe it's 0, maybe it's not. That becomes the memory address. You go and get the data. So we've got 3 modes to go get data. We got 2 more to go get the next instruction, and their names are PC relative if you're branching, pseudo direct if you're jumping. Only 5. That's a RISC machine for you. CISC machines will sometimes have 20, 30, or more addressing modes, okay? Very complicated. The control to do those becomes burdensome and large and slow. All right, great question. Thank you. At first I misunderstood what your confusion was. In the end, now I know what you know. He was asking, how do we address where we want to go to if it's branch? Answer, PC relative. How do we address where we want to go to if it's jump? Answer, pseudo direct, okay? How do we address the data we want to go get if it's an immediate addressing? If it's a load or store, base plus displacement addressing. If it's a R-type, register addressing. There we go, 5 addressing modes. Good, good, good review over the ISA. Okay, we're actually trying to implement the ISA here, but I can see that there's still some missing points in the definition of the ISA. It's good to go back, because if you don't know what you're implementing, how in the world are you going to implement it? Good. All right. What's your name on the corner of the back row? Esen. Emerson Esen. Are you good? You're understanding? 80, 90, 95% level? Good, good. Okay. Fulya Naime, or Naime Fulya. Are you good? Are you understanding at a high level? Good. I'm glad. Are you better now than when you came in the door today? Yeah, and I'm not talking about physical health or emotional well-being. I'm talking about, your understanding of the topic. Are you further ahead now because we did this hour? I feel like it was a pretty productive hour. I feel like we covered a lot of things really well, and we've got a much more solid foundation to go forward. We're going to do the control unit in the next hour. So get a good 10-minute break, get some air, get some walking. Don't put any tobacco or tobacco products in your body. Get some water, get some fresh air, and come on back in 10 minutes, okay? All right.